So, in many situations, we'd like to create networks consisting of large numbers of non-overlapping brain regions. So network analysis tries to characterize these networks using a small number of meaningful summary measures. So we might take a big network and try to summarize it using a few summary measures that we can compare across subjects or groups. The hope is that the comparison of these network topologies between groups of subjects might possibly reveal connectivity or abnormalities related to neurological or psychiatric disorders. To recall, networks can be represented using graphs, which are mathematical structures used to model pairwise relationships between variables. They consist of a set of nodes or vertices V and corresponding links or edges E that connect pairs of vertices. So a graph G, which is equal to V and E, which is the collection of the nodes and links, may be defined as either undirected or directed with respect to how the edges connect one vertex to another. In addition, the edges may be either binary, just 0, 1, or weighted depending on the strength of the connection. It's generally beneficial to represent a brain network using an n by n matrix where n is the number of nodes. Here the graph nodes are represented by columns and rows of the matrix, and a link between two nodes I and j is represented by matrix element ij. Here's an example of a network. So this is a bidirectional network between three different nodes A, B, and C. We can write a connection matrix as a 3 by 3 matrix where pi AB represents the strength of the relationship between A and B. So this will be both in the AB and BA element because it's bidirectional. And pi BC is similarly the link between B and C. Again, because it's bidirectional, we have an element in both the CB and the BC element. An adjacency matrix is just a binary form of this, which takes values 1 if there's a connection between two nodes and 0 otherwise. And here we have 4 ones, one corresponding to the BA, another to AB, then one to CB, and then we have to BC. So before doing network analysis, we have to construct the network. And the basic steps of network construction include first, defining the appropriate nodes, then performing network estimating or estimating the connection matrix between the different nodes. This can be correlations or partial correlations or whatnot. And thereafter, one thresholds the resulting connection matrix to get an adjacency matrix. Once we have the adjacency matrix, we can create the networks and we can analyze it using network analysis. So after constructing the network, we're going to want to quantify parameters associated with network topology and efficiency. So any given network measure may characterize one or more aspects of global and local brain connectivity. These include aspects of functional integration and segregation, and the ability to quantify the importance of individual brain regions and test the reliance of the network to insults. So we might want to look at whether or not a certain brain region is a hub of activation or whatnot. Here's some basic notation that we're going to be needing. So let's let little aij represent whether there's a connection between nodes I and j. So aij is equal to 0 if there's no connection, and aij is equal to 1 if there is a connection. So the degree of a node is equal to the number of links connected to that node. So let's look at this little cartoon image to the side here. This is a little network. Here, A has degree 3 because it's connected to 3 other nodes. D also has degree 3 because it's connected to 3 other nodes, A, C, and E. But B and E, for example, only have degree 1 because they're only connected to a single node. C, finally, is connected to 2 nodes, so it has degree 2. The next piece of notation is the number of triangles around node I. This is defined as follows. So here, A has 1 triangle because you'll see that we can go from A to D to C and then back to A. So in 3 steps, we can return to A. So this is basically showing a single triangle A, D, and C. The shortest path length between nodes I and J is defined as Dij. So for example, the shortest path length between A and E would be 2 because we always have to go through D to get to E, and that's the shortest way to get from there. So now we're going to use these pieces of notation to define different network properties. The first one we're going to talk about is the clustering coefficient of the network. So the clustering coefficient of the network is defined as follows, and it depends on the number of triangles. So Ci in this case represents the fraction of a node's neighbors that are also neighbors of each other. Basically what Ci measures is the number of triangles that you have normalized by the total number of possible triangles. This is a measure of functional segregation in the brain and represents the ability for specialized processing to occur within densely interconnected groups of brain regions. Another network metric that we often use is the characteristic path length of the network, where Li is the average distance between node I and all other nodes. So this is just basically the average of the average distance between node I and all other nodes. This is a measure of functional integration in the brain. So this represents the ability to rapidly combine specialized information from distributed brain regions. Here let's look at our example network again and look at some of these network metrics. So here's the network, and here's the adjacency matrix, and we see it's either 1 or 0. 1 is if there's a link between the two nodes, and 0 if there's no link. Here's an example of the degree distribution. So as we saw before, 40% of the nodes, so 2 out of the 5, have a degree distribution of 1. So that's B and E. They only have a single neighbor. 20%, or 1 out of the 5, has a degree 2. And that would be, in this case, C. And then finally, 2 out of the 5 have a degree network of 3. And that's A and D in this example. If we look at the clustering coefficient, again, remember, for each node we can calculate it's the number of triangles divided by the total number of possible triangles. So A has a A's contribution to the clustering coefficient is 0.33. There's one triangle, the ADC triangle, but there's 3 possible triangles. One is the ADC triangle, but another would be the ABC triangle, which doesn't exist in this case, or alternatively the ABD triangle, which also doesn't exist. So only 1 out of the possible 3 triangles exists, so A contributes 0.33 there. B has no triangles, and so that it contributes 0. C has a single triangle and only 1 possible triangle, so that contributes 1, etc. So then we take the average of those and we get the clustering coefficient C, which is equal to 0.33. And so this represents how connected the network is. If we look at the path length, here we can see what's the path length between B and A? Well, it's 1. What's the path length between C and A? It's 1. D and A, it's 1, and E and A, it's 2. And then we can do this for each of the different unique combinations of nodes, and we can take the average of this, and the average path length is 1.6. So this tells us a little bit about how quickly we can move within the network. There's lots of different network types, and they have different clustering coefficients and different path lengths. Here we see the example of a dense network, a fragmented network with little sub-networks split up, an ordered network, which is very orderly structured in a very fine-grained pattern here. We have sparse networks, connected networks, and even random networks. One particular type of network that we often talk about are small world network. And so the brain is thought to optimize information transfer by maximizing functional segregation and integration by minimizing the wiring cost. And small worldness is used to describe a design that enables distributive processing and regional specificity. Conceptually, a small world network is more clustered than a random network while still having approximately the same characteristic path length. So once we compute different graph properties, we often want to interpret these graph properties. And 2 common means of interpreting graph structures are by comparing to a benchmark network. So we might test whether or not the graph properties differ from, say, a random network or not, or comparison to other real brain networks. Maybe we want to characterize different network properties from, say, networks computed from schizophrenics versus healthy controls. So network analysis has received much attention in the neuroimaging literature in the past couple of years, and it's really one of the hottest areas of research at the moment. There exists a number of metrics for describing various characteristics of a network. We've only touched upon a couple of them just to give you a flavor for the type of analysis that one might do. And the hope is that this can shed light on how certain disorders affect the brain. Okay, so that's the end of this module. Here we've talked about network analysis, and in the next couple of modules we're going to start talking about affective connectivity. Okay, I'll see you then.